Hi, Mr. Pierce here again. This is our second video in our introduction to differentiation. In the first one we looked at the curve y equals x squared, and what we realized is that when we had certain coordinates on that curve, in particularly the x parts of the coordinates, then we could easily find the gradient by doubling the x coordinate. So if when x is minus 2, we know the gradient is going to be minus 4. When x is minus 1, it's going to be double it, so it's going to be minus 2. Double 0 is 0, and it's going to be 2 and 4 here as well. So when we have the x part of the coordinates of the curve, then it's quite easy to find the gradient. And of course we could write that out as an equation now, because the pattern's quite easy. The gradient, sorry for the bad writing handwriting there, is equal to 2 times the x coordinate, so 2x. Okay? Obviously, instead of writing out gradient every time, we don't want to do that every time. So instead of writing gradient, we're going to use certain notation. We're going to say dy by dx. And the reason we do that is because in the 17th century, when Gottfried Leibniz, was thinking about differentiation and doing it for himself, this is what he used for the word gradient instead of writing out the whole word. He used dy by dx. Okay, so the gradient function for y equals x squared is dy by dx equals 2x. And the reason I say this is a function, because obviously x can change, the x coordinates can change. If x is 10, then the gradient is going to be 20, because 2 times 10 is 20. So this is called the gradient function. It helps us find the gradient at any point on the curve. Here, I've written down y equals x cubed, and I've also given the table, and for each x coordinate I've given the gradient at that particular point. So what you might want to do now as an interesting exercise is try and think about what the gradient function would be for this particular curve. So how do you get from x to the gradient? What do you have to do? That will help you find the gradient function. So you might want to pause it here and try and do that yourself before you replay the video. Okay, so we're back on, for this particular function, I can tell you, hopefully you managed to figure it out, but for this function, the gradient function, dy by dx, is actually 3x squared. And just to show that to you, when x is 2, then we've got 2 squared, which is 4, times by 3, which does in fact give you 12. So this particular gradient function does give you the gradient for all of these coordinates here on the curve y equals x cubed. So now we've got the gradient function for x squared, we've got the gradient function for x cubed, and I can also tell you what the gradient function for y equals x to the power 4 would be as well. The gradient function for that is dy by dx equals 4x cubed. Okay? So hopefully now you might be starting to see a pattern in the gradient function. Of course, when x squared is 2x, x cubed is 3x squared, x to the power 4 is 4x cubed. So hopefully you realize that what's actually happening is the power is coming down in front of the x and then being reduced by 1. So then we take away 1 from it. So for example, with y equals x cubed, we bring the power down to get 3x, and then we take away 1 from it, so it's actually 3x squared. Okay, so and also with x squared, we bring the 2 down to get 2x and take away 1 from it, so 2x to the power 1. And of course this is 2x to the power 1. So in general, what we could say is for a curve y equals x to the power n, for any power, then dy by dx is n, if we bring the n down, n times x to the power n take away 1. Okay, and that's quite a nice rule for these particular type of functions. This rule doesn't exist for every function, but for these particular types of functions it does exist. So I hope that helps, and we'll continue differentiation in the next lesson. Thanks a lot. Bye.